Hello everybody. I am Hélène Gonin, the event manager at John Group, and welcome to this new Analyst Thursday webinar. Today, you're going to have the opportunity to spend the next hour with our analyst team to discuss about data centers and how AI is transforming them. We're going to have three speakers to do this webinar. Mike Howard, VP of DRAM and Memory Research, John Lawrence, Senior Analyst in Computing Activity, and Martin Vallo, Photonic and Lighting Senior Analyst at Yole Intelligence. No more waiting. Mike, let's start the webinar.
Thank you, Elaine. Today we are going to discuss the changes at the data center, particularly those changes that are being driven by the introduction and growth of AI. Focusing primarily on the hardware side of things. And the 800-pound gorilla in this space is clearly NVIDIA, as witnessed by their recent financial performance. And with that, I'd like to throw this over to John, who focuses on CPUs, GPUs, to discuss what's going on with processing in the data center.
Thanks, Mike. I just came back from Computex in Taipei, and the NVIDIA Q1 result had just been out for not even a week, I think, at that point. And Jensen gave the one of the keynotes, and everywhere you looked, every single vendor was trying to say how they were relevant to the NVIDIA story. Naturally, OEMs were showcasing their server builds, and here's where the GPU goes, and here's where Grace Hopper goes if you're building that kind of server. But also the even the power supply guys were showing, okay, if you're going to build a server with 100 GPUs in it, here's the power supply you're going to use. So it was interesting to see that everyone at this conference, even those that are just minorly tangentially related to data center acceleration, AI in the data center, were riding NVIDIA's coattails on this, and it's with good reason. NVIDIA really blew things off the doors, so to speak, off the hinges. Blew the doors off the hinges in their last earnings. And so what's going on with that? So what I'm showing here is a piece from the processor monitor where we track CPUs, GPUs, application processors, and FPGAs, but really focusing on the GPU market. You can see back in 2019, this is a $10 billion market, and just in a matter of a couple of years, that more than doubled. Most of that was on the client side. Most of that was in graphics processors for gaming or the crypto mining space, also using those same flavor of GPUs. But you notice the server piece has been growing through that time as well. And even into 2023, things kind of slowed down, but the server piece still stayed strong. And that's the main story behind NVIDIA. So talking about their quarterly revenue, we saw Q1 23, they're back up at 7 billion, which is a level they've been at before. But we look at what was happening all throughout 2022, that client piece, everything that's not data center, the gaming came way down. It used to be more than 2/3 of their business, came down to 1/3, but the data center held nice and strong through that period. And what's going on there is, of course, what we talked about in the intro. It's AI and acceleration in the data center. And I highlight here they guided 11 billion for Q2, which is mainly why there's such a big financial story. Gaining, 200 billion in market cap in a single day is off of that guide. So it's really interesting to see how they're capitalizing, and they're the first one in this space, not first one in this space, but they've got the strongest portfolio in this space right now. The CUDA software is a big piece of that, giving their customers the tools they need to accelerate all sorts of workloads, especially these large language models that we're hearing more and more about with things like ChatGPT. If we look at like a normal server, how are these put together? It's kind of for your average consumer, or you're more someone who's not tech focused. This may not be well understood. So maybe just to illustrate, a server can, we think of that as existing on a single motherboard. And on that motherboard, you may have 1, 2, or 4, or even 8 CPUs. Generally, it's 2 in most instances. And then you'll have some combination of these other components. You'll have DRAM, you'll have some SATA, you'll have some SSDs. Depending on the workload, depending on the application, you'll have more or less of these kinds of, or in some cases, none of these in certain instances. But what I want to focus on here is on the acceleration card piece here. This is, we label these here as either FPGAs or GPUs. Really, in these AI-centric workloads, especially the ones that the large language models like ChatGPT have been trained on, they're sending 8 GPUs onto a single server. So that server has 2 CPUs and 8 GPUs being used to train, and they have hundreds of these servers all working together to train the model. So that's where you can see that this is in this world where there's maybe 14 million servers shipped a year. You start to get a few of these that are a few percent of these that are used for AI training. You start to see a huge multiplicative effect on the shipments of GPUs into servers.
Hey, John, real quick, why are GPUs so valuable for AI workloads specifically? Why not just use more CPUs?
So good question, because the GPU architecture originally developed for accelerating graphics. It's a highly parallel vector multiplication kind of application. And that's the same sort of application, same sort of arithmetic, so to speak, that needs to happen in order to train the parameters within the matrix math of doing a large language model or other machine learning models. So in fact, what's interesting is, so for training, especially in the cloud, training a cloud-based AI, generally the hardware of choice is GPU. But up until recently, the inference hardware of choice has still been CPU. So training is setting those parameters in the model. Like, think of that as, if we're talking about object detection, think of that as sending millions of thousands or millions of characterized images into a image classification model. And then the inference is the quick, just checking what one thing is to against the model. What is this? So in a image classification model, it's easier to talk about those. That's like, okay, what's this image? And the model spits out, oh, that's a cat. Okay. So in general, prior to the last, call it 6 months, most of that training is done on GPUs, highly parallel kind of work. You can do all that work. It may take a number of days or weeks to train a model, and then your model's trained and you don't need to use those GPUs anymore. They can be utilized for something else. And then CPUs will be the workhorse for the inference on that model. Well, with large language models, ChatGPT specifically, and some of these other generative AI pieces, the inference work is heavy enough that they're using GPUs on that side as well. So whereas GPUs were the training workhorse, now they're being used in both places. And this is just coming because of the size of the models. And I think if we were to chart through time, these models have been growing, I don't know, 10x over a span of just a number of years.
Generation to generation.
Exactly.
Okay. And so is this something that did AI come to the GPU, or did NVIDIA move its architecture towards AI, or is it just coincidental that NVIDIA happened to have the best product for AI? Do you have any sense of that?
Yeah, so NVIDIA did a lot of work in the software space to enable their hardware to be critical for these high performance compute applications. So I would say they were pretty prudent and strategic on setting up CUDA to be that tool, and they've been working on that for I think we're coming up on almost 2 decades of working on that. So it's they are in that space, and they have a ton of learning on that, and they have teams of engineers to help their customers. Customer comes to them with an AI problem, and they say, okay, well, we can solve that, and here's how we've solved that in the past for someone so and so, and here's how we can do it for you. So that's the challenge for some of the other players is, like for instance, Intel and AMD, they have good hardware too, good, really fast accelerators and powerful stuff with Ponte Vecchio and MI250, MI300 coming out of AMD. But I think the piece that they're behind on with NVIDIA still is the complementary software package and API that can be used to work with that hardware.
Okay, and not to derail you too much, but so what's the bigger moat? Is it NVIDIA's sort of hardware lead or hardware architecture or hardware prowess, or is it NVIDIA's sort of software, or is it the combination of the two? Because clearly, they've got 80+% market share in this space. I guess maybe it's a better question to start with, do they have a real competitive advantage? And sort of where do you see that competitive advantage sort of rooted? Is it more on the software side or hardware or combo?
It's more on the software side.
Okay.
Their hardware's not to say their hardware isn't great also, but the software side is what's made their tools easier to integrate for customers. And then once they have a critical mass of customers. I mean, they have the massive customers. That becomes a perpetual kind of inertia around if someone new in the AI space says, okay, where should I look for my AI solution? Well, these 100 other customers have already chosen NVIDIA. Seems like I should go that way. So it's a little bit of they already have that market inertia behind them. The thing with this current boom is that maybe they won't be able to satisfy everybody with their hardware just from pure supply demand. So there's a chance, there should be some opportunities opening up for Intel and AMD still. And AMD's not to say that they're not in. They're in. I think they're in the fastest supercomputer to date. Maybe have to check that most recent data point, but they were in Frontier announced last year, so that's the first exascale supercomputer.
Okay, and so clearly, if you're a new customer coming to this space, you want someone else to do some of this initial heavy lifting. But we have seen a trend of particularly the large hyperscalers sort of developing their own silicon, not just for AI acceleration, but for all kinds of workloads. Is that perhaps the chink in the armor for NVIDIA that maybe an AWS or a Google figures or keeps leaning into their own silicon to try and, because the prices that I've seen for some of these NVIDIA products are pretty steep. What do you talk to me about those risks there?
Yeah, absolutely. I mean, the hyperscalers, they're the ones for whom the economics of build versus buy get a little bit more interesting, I'd say, because they have the engineering tools at their disposal to build something themselves, and they also have the luxury of being able to tailor the workloads in such a way to work on their custom silicon. So that's kind of why you've seen AWS, for instance, go their own route on CPUs, pushing into something that's ARM-based into their data centers. On the acceleration side, you can see something similar happening. Yeah, it's certainly possible. It's for us, the hard thing is it's the interest is there right now, and you can if you're a hyperscaler, granted they all got projects in play. Those projects need to be delivering something right now, and if it's not delivering something right now, then they'll go load up some more nodes on NVIDIA. So it's kind of the it's kind of for them.
Okay, good insight. Thank you.
We want to talk a little bit more how this is driving overall processor revenue in the data center. And so as a percent of total here, we're like, back in 2019, there's only 10% of overall processor revenue in data center was for GPUs. If we look at where it is now, it's about 30%. And with this trend, and we expect that to keep going, we see this going up to not quite 50%. Mike, your last question though is pertinent. I mean, this is assuming that that GPUs maintain about 80% of that acceleration workload. If that cuts down into the 60% range, then of course more of these custom ASICs are taking that away from GPUs. But even then, it's still a massive growth story versus the 10 billion, the 3 billion we had back in 2019. Beyond the 10 plus we had in most recent times.
Well, and perhaps also it's not going to CPU, right? It's right. On that last chart, that salmon segment that you had there, whether that ends up being GPU or custom ASICs is still to be determined, but it's still going to represent that total bar.
Exactly.
Okay.
Yeah, and in fact, I mean, and the servers all need CPUs anyway, so CPU, I guess, still gets to experience some growth here. But the real potentials in that coprocessor acceleration realm. And so, for example, here, this is how we've got it, how we're thinking about the overall server markets. So this is the chart on the left is total servers shipped, and showing the portion of those servers that we see with acceleration coprocessors. So it's right now it's maybe just under 10%. That number is growing, and we were still challenged in some cases that our growth up to 18% was too aggressive, and I'm not sure that's even aggressive enough. But the thing is it's maybe a doubling of that penetration of servers that have coprocessor acceleration. And then within those accelerated servers, if 80%, like I said, 80% of those satisfied by GPUs, that's where that's the math behind getting to a GPU, a data center GPU market that's pushing into the $30-40 billion. It's
that brings up an interesting point. From a DRAM perspective, the memory that we see going or being sort of attached to those GPUs is HBM, which is several times more expensive than traditional DRAM, so big dollars there. In addition, there's even more system memory, so just the memory footprint goes up. I've seen some pricing on some of the new NVIDIA products in the hundreds of thousands of dollars. Clearly, these servers are much more expensive than sort of traditional enterprise servers. But I think the point needs to be made that AI will drive significant value, and that's why the economics of this work. We're not spending the same dollars that we were 10 years ago on servers, because those dollars that we spent on the sort of server infrastructure 10 years ago led to a certain revenue stream. I think it's worth pointing out that the anticipated revenue stream from AI is an order of magnitude greater, and that's why customers are willing to. I mean, John, how much are they spending on these GPUs on a per server basis? Do you have a sense of that?
It's hard to pin down, but for like these A100 or H100 based systems, we've got it expecting it's like 10 to 20 grand per GPU, and you've got 8 of them in a single server, so it scales up pretty quickly, and it really outshines the BOM portion that is attributed just to the CPU. So it's substantial.
Yeah, but an overall tailwind really for all segments. That's I think part of there's a lot of strong narrative around GPU sort of eating the world, but let's remember all segments are riding on the coattails, to your earlier point, the coattails of NVIDIA, in that as NVIDIA sells a server, they also take along 20 or 30 grand worth of DRAM with them. They also take on a larger storage footprint. They're still taking along CPUs. Clearly, if customers weren't seeing value in spending $250,000 on a server, they wouldn't spend it. And so that's part of the, because I get a lot of pushback on the DRAM side when I show sort of the content going into an AI server and the cost of that. And people are like, there's no way people are going to spend 10 or 15 or 20 grand on DRAM in a server if they're only spending half of that today on the entire server. But then the counter argument is, but the value creation is there. And so that's why people will spend money on that. And I think it points to the overall sort of semiconductor industry, when do we hit $1 trillion? 2030 has been thrown out as the year when we finally hit $1 trillion. I think the developments in AI of the last 6 months, I think everyone's a little bit more bullish on that number now, because it's clearly there's value there if AI is the vehicle to drive that growth. Anyway.
Yeah, to think about the value that it brings, like you've played around with ChatGPT, right? So pretty impressive. Imagine wiring that into different applications. And so rather than me going over to my ChatGPT tab and asking it some clever questions, and have it replace any of the help functions within other apps, or not even the help functions, but just the search functions within other apps, and it starts to get really interesting on how this starts to add value to other pieces of the economy and especially in the you mentioned memory. I think it's worth looking at. No, that was your slide. Here we go. So we had this, and I want to point this out. This is taken from one of our fine teardown reports here at YOL. We our sister organization YOL System Plus. They open up lots of different components, a lot of different systems. And this is from when we opened up an A100 from NVIDIA. I think they're working on an H100 right now, so pretty interesting stuff coming. But look at, that's a massive HBM stack, 8 high with the GPU all on a 2.5D interposer, silicon interposer. How does that the content in one of these compared to the overall content, DRAM content in the server? Is it?
Yeah, so obviously configuration is the key there. Are they loading this with 4 cards, AICs, or is it 8? But you're looking at 100 gigabytes roughly per card, and that number always growing. And if you're sticking 8 cards in, all of a sudden you're pushing up on a terabyte of HBM. And if you could skip to slide 14 real quick. HBM is a pretty amazing technology, as John showed in the diagram there. It's all connected through TSVs. Key about TSVs is it's expensive. It's still very difficult work to do. It's difficult to stack those die. Yields are challenging. So prices for that material is really high. And it's much less of a commodity. You're going to get designed into a socket, and you're going to really have control over that socket as a supplier for a long time. So it's for the memory suppliers, HBM is a really attractive market to get into. And so there's that element of it. HBM is super high performance. To your earlier point, why is GPU winning? It's because it's so highly parallel. No surprise, HBM is a highly parallel memory as compared to traditional DRAM, sort of order of magnitude more parallel than traditional DRAM. And if we look at sort of the growth of memory in the data center, look, traditional servers are still going to be the lion's share of the market. John, you showed a chart showing AI sort of work or servers hitting sort of that high teens of total server sales. So, we're still looking at 85% of servers going out the door as non-AI accelerated servers. So that's the blue column on this chart, still growing. That DRAM is growing sort of in the mid 20% year on year. AIs are doubling that. And truth be told, I'm probably overly conservative on this. But a lot of that, more importantly, this is on a bit basis, a lot of that is HBM. And so those dollars are accelerating even faster. So, AI, again, clearly NVIDIA is the big winner here, at least for the foreseeable future. But the growth in AI is dragging or lifting everybody up. DRAM suppliers are going to see a tremendous tailwind from AI, and it's a more stable market. We've seen a lot of turmoil over the last handful of years. Part of it kicked off by COVID, as we saw different segments rise and fall. The AI demand is, a lot of it, first of all, is more of a corporate type demand, which spending is a little bit more stable. And it's easier to build a business around, as opposed to sort of consumer spending, which is a little bit more fickle and more dependent on the ebbs and flows of the economy. So AI, massive tailwind for memory. In particular, it's going to be a massive tailwind for HBM. And there's, John, I asked you a question about the sort of defensiveness of NVIDIA's position. Clearly, they've got a strong defensive position between their hardware and their software. The memory suppliers, there's three people that build HBM in the world. Will there be a fourth? No. So there's more competition there, but there's very little opportunity for anybody else to break in. So it's a slightly different dynamic from a competitive perspective. Unlikely to see anyone else enter this space, but the three incumbents are certainly going to bring their best competitive behavior to this space to keep price. I mean, we don't expect the sort of pricing premiums to continue to accelerate in the HBM space. They're going to continue to get a premium for that product, but it's not going to overall depart long term from the overall DRAM market.
Is there, sorry to stop, is there still a strong HBM play in the if more acceleration goes towards custom ASIC silicon?
Yeah, I mean, if you look at TPUs or some of the other custom options, they're all leaning on HBM. Again, it's all highly parallel. The workloads don't change. Just the workloads might be tweaked because the underlying logic silicon is tweaked, but that it's still highly parallel. You're still running these multi-billion parameter models that are highly parallel, and you need to hold all those weights at the same time. And HBM right now is the best solution for that. We've obviously, this discussion is about the data center, and one of our underlying sort of, I think, thesis is that it's going to be AI is going to be data center driven, at least for the next handful of years. But we do get a lot of questions around edge. Well, how does the edge play into this? Because latency clearly takes a hit when you're having to go in and out of the data center. Pushing stuff to the edge as far as into your handset certainly seems like a development we will see, at least in the sort of longer term outlook. Whether that's in the 5-year forecast or the 10-year forecast is still to be determined. HBM right now doesn't play well though, sort of on a handset type device. So I think that for things to really push to the edge, we're going to need to see some changes, particularly around power consumption. We're going to need to see some changes around that. John, that bringing up of power consumption, I've read a lot over the last 6 months about the sort of country-sized or country scale power consumption of some of these applications. What are your thoughts on that? How do you see that developing?
Yeah, it's significant, and I think that's one of the factors that NVIDIA competitors are trying to grab onto, is to say, okay, well, look, we can do this many tops, but at a lower watt point, and try to move that direction. I think peak TDPs right now are in like the 700 watt range for a single card, and that's up from the last generation, up from the previous generation. So even though all the design and engineering teams are aware of that, the implications of that, it seems the choices so far are still to go, yeah, well, to improve our tops per watt, we're going to keep chasing much higher tops, and see how the denominator plays along. There's some interesting things we've seen that are, I don't know if they have much market presence yet, but for instance, architectures more that are neuromorphic based can be something that consumes less power, and there's a little bit of that coming into the data center as a neuromorphic accelerator. That would be an event-based, so it's not necessarily running. It's not running everything all the time. It's okay. Something's happening. We spend the resources to address it, and then kind of shut things down. So it brings a more mobile mentality to the data center. But still, I mean, these data center workloads are somewhat, to your earlier point, someone's willing to spend a $250,000 on a single server because they intend to run it for 24 hours a day. Yeah. So that will generate a lot of heat and dissipate a lot of power.
So let me bring Martin in here. Martin, what's your perspective on this more broadly about photonics, interconnects, and perhaps even how power plays into your area?
Okay, so yeah, the photonics enter to the data center computing heavily with the so-called co-package optics, or yeah, especially they use different names for the processing application. But let me give you some insights into this topic. So actually, co-package optics term, or CPO, is more linked to the switching or networking applications, as well as the near package optics or OBO optics. CPO is a technology that addresses some challenges which were created by pluggable optical transceivers, including the thermal management issues, high bandwidth, latency, as well as the pore density and power consumptions. Yeah, however, there are different and cheaper alternative ways that can enable the data center to scale for 50 terabit or 100 terabit switching capacities. We can use the different network architecture, or we can change the system design of the switch line card, or we can integrate the new materials into the pluggable optics. So although initially the CPO was considered the only way to reduce the power, as of today, the power reduction can be achieved by both technologies, CPO as well as the pluggable optics. But what's the situation in a computing? So AI models require the insatiable demand for compute, storage, and data movement, and the capabilities of the traditional architectures create the main bottleneck for scaling of future ML systems, right? So, and as a result, the optical interconnects for very short reach applications have emerged, particularly for high performance applications like AI ML. And the industry calls this technology like the in-package optical I/O. So in-package optical I/O for XPUs, memories, or storages can help to achieve the low latency and high bandwidth required for these specific applications. Moreover, the potential of billions of the optical interconnects in the future is driving the big foundries to prepare mass production of silicon photonics chips and accept the different types of designs, especially the photonic integrated circuit design from different design houses. So here we have a analysis of evolution of the optical interconnects based on the transmission distance within the data center. So in current networks, most of the links within the racks are copper, and as the data rate increases, the copper links will need to move to the optical, and to support the explosive growth of AI ML application and data volume, the optical interconnect will need to go to very short reach applications, and the scale out architectures will be are enabled by the high bandwidth, ultra low latency, and low power consumption. So now let's take a look what is actually optical I/O for infrared applications. Basically, the idea is to bring the optical connectivity to very short reach applications, mostly within the system or within the rack. And currently, many changes stem from the using of electrical inputs and outputs, right? And the applications such as AI and ML require to move data rapidly from chip to chip or from board to board, and consequently the computing chip need for communication either higher number of pads or ultra high speed per single pad, right? And additionally, the data movement power is the primary driver to increase is the primary driver to increase increase of the power in a server chip. So in package optical I/O used for different XPUs or storages and memories is coupled with the packaging innovation in a form of the chiplet, as we can see on in the figure in the top in the top and in the middle. So the optical solution can provide 1,000 times more bandwidth at the 1/10 power when it compared to the electrical iOS solution. So most of the optical iOS solution will use remote or external laser source, which provide more flexibility and the space for replaceability of this key component.
Can I ask
Yes.
a quick question? So if I heard you correctly, it's a 1000x bandwidth performance versus traditional architectures and a 10x reduction in power on a per operation basis. Is that right?
Right.
And so that can't be free. What sort of additional costs might one incur using optical I/O versus copper?
Yeah, obviously at the beginning, the solutions will require the higher cost, but as you discussed with John just a few minutes before, it brings a big value to the servers, particularly for AI applications, and the companies are willing to invest more. But yeah, for the next generation systems like the NVIDIA build, we think that that there will be the both technologies, optics and coppers as well, and that they will coexist for some time. But yeah, for next two generations, we think that the optical I/O heavily change the copper links, say, in the systems for high-end applications, of course.
So initially, what do you have an idea of what sort of like for like price premium we might see for optical I/O versus copper? And do you expect that price premium to diminish over time?
Yeah, we expect that the cost might be around. Yeah, the goal is to get below 1,000, maybe even below $800 per chiplet, right? But it's difficult to define the price per optical I/O chiplet because it can provide multiple lanes inside, multiple links inside the chiplet, and this way it provides some kind of flexibility to decide of the user what is the bandwidth for the chiplet and what is the data rate per lane. So it's difficult to stick with one price tag.
Okay, tough comparison. Okay, thanks.
Okay, so now I'd like to explain a little bit the type of applications which are expected for optical I/O technology. So basically, three technology areas have been considered for the coming applications. The first is the physical interface between the optical I/O chiplet and the system on a chip. The second is disaggregated architecture, kind of resource pooling, and the third is in-memory computing. So it's related to the memories. And yeah, these disaggregated designs distinguish the compute storage and memory which can be found in a servers, and pulls them separately, right? And using the optical based interconnects by means of optical I/Os can help to achieve the necessary bandwidth and very low latency. So, and in the time slide, we can see the timeline analysis of bandwidth scaling roadmap of optical I/O chiplets. So the optical the TeraPHY technology developed by IR Labs today provides the communication bandwidth 2 terabit per second each direction, and the shortline bandwidth is 200 gig per second. And we expect that the shortline bandwidth 1 to 10 terabit per second per millimeter can be available by the end of the decade. Yeah, some of the users have more optimistic expectations that the shortline bandwidth of 20 terabit or 50 terabit per second per millimeter can be achieved earlier, but we think that this is too aggressive. So now let me sum up the market status of the different integrated optical solutions. So the last year in 2022, the market with the integrated optics reached around $38 million, and the optical I/O reached around $5 million. So this year can be considered as a year of shipping low volume of these systems for testing, right? But we estimate that next 5 or next 10 years, this market will grow rapidly, mainly due to the demand for optical I/Os for high performance computing, and it will reach $2.3 billion at CAGR of 81%. So, which is enormous growth, which will be driven mostly by the demand of the computing companies like NVIDIA, AMD, and then the hyperscale data center operators.
Oh, yeah, I got a question for you.
Okay.
So if we go back to your slide 21, so Martin, is there anything on the roadmap here that's at risk? Are there any technical developments that need to happen in order to hit this roadmap? Just trying to figure out because a technology like CXL, which you called out earlier on one of your slides, clearly right now the big handicap of CXL is the latency that it faces as compared to traditional system memory. And we are looking closely at CXL as really unleashing a lot of potential demand, just because it enables customers to load systems with much more, not only adding cards, but also just raw DRAM. Part of that, though, and part of that growth is going to be really dependent on the interconnects. And so love to understand what your thoughts are on potential risk in this forecast.
I think this is rather conservative forecast, so we don't expect that the main players will need to achieve some big breakthrough, but obviously they need to improve the manufacturing yield of the silicon photonics chips. I think that they will need to focus on design of the future modulators, because this is the big part of the optical interconnects. And then yeah, there is the continuous work on a laser side, on the light source. So and yeah, the light source suppliers clearly drawn their roadmap, and I think it's it's feasible to reach this bandwidth scaling roadmap of the optical I/Os here. So nowadays, I don't see any big risk to achieve the higher data rates and the higher throughput.
Okay, great, Martin. Thank you for that. Clearly, AI has come on much faster than I think many people thought over the last 6 months. ChatGPT really kicked off an amazing amount of enthusiasm and interest in the space. It is fundamentally shifting how data centers are built and really the value that data centers can bring. As we look at this space, we're constantly trying to evaluate, does data center remain sort of the center of the AI world? Do things push to the edge? Obviously, that will have an impact on everything that we've talked about today. But for the time being, and at least the near future, it looks like data center is going to rule as far as developing AI, not only from the learning, but also the training and inference. So been great to talk to you all today. I hope you've gotten a lot out of this and look forward to talking to you next time. Thank you.
Okay, thank you, Mike. Thank you, John and Martin, for your presentation. Very interesting. As you can see on your screen, we have many products related to the topic we covered today. It's going to be a pleasure for us to answer your question about it if you have some. I'd like to thank you all for your attendance today, and I'd like to give you some information about the presentation and replay. You can find them on our website, and you can watch it again for more information. Obviously, we have a new Analyst Thursday on July 6th about semiconductor test with John West and Lin Liu, and it will be a pleasure to welcome in July. Thank you again for your attendance, and see you soon.